This is a tesseract undergoing 4D rotation in Minecraft made using block display entities. And in this video, I'm going to show you how they work and how I made this. So what is a block display entity? To put it simply, it's just an entity that can display a block. And you can summon it with commands, and you can specify its block state. In this case, I chose a diamond block, but it can be any block in the game. Now, block display entities can also undergo something called transformations, which makes them appear different. And by default, these are the four ways to do it: scale, right rotation, translation, and left rotation. So if I change the scale in the first term, then the block will be transformed in the x-axis, and so it will appear longer. Now, there's another way to undergo transformations, and it's called quaternions. And this is what it looks like. It's 16 elements in a matrix that determine how the block will be transformed. And I know this is quite hard to see, so I took the liberty of visualizing it. So what are we looking at here? Well, the first row indicates transformations along the x-axis, second y, third z, fourth w. We can ignore w for now. I'm just going to show you how interpolation and rotation work in the three-dimensional space. So if I want to transform something, say I want to stretch it along the x-axis, I pick the first four terms and I transform the one that is first, like this. And I'll get the exact same transformation that I got over here. Now, what do all these numbers actually mean? So how it works is each number specifies how many blocks to stretch the block, and each column specifies which axis to stretch it in. So for the first term, where it's 1, it's being stretched 1 block from the origin in the x-axis. If I were to change one of the other ones, say for instance y, then what it would do is it would stretch it 3 blocks in the x-axis, choosing the y-axis to do so. And if I was to do it in z, let's just change a smaller number, it will stretch it 2 blocks in the x-axis using the z-axis. So that is how transformations work with regards to stretching. There is also translation, just like in transformations, and it's all done using the last 4 terms in each row. So let's set this back. If I change, say, the 8th term, which is the last one in the y row, to 4, it will translate the block 4 blocks up from the origin. And that is just about everything you need to know about quaternions. Now let's talk about interpolation. So as you've seen, a transformation transforms a block from its original state to a new state, either one of these. So you can actually make the game do this smoothly, and it's called interpolation. It interpolates the missing values of the translation or transformation. So in order to do this, you actually need to do it in 2 steps because it can't be done instantaneously, unlike transformations. So usually just a repeater and a data merge command will allow you to merge interpolation into the transformation. So the numbers are measured in ticks. So for 40 ticks is 2 seconds because there are 20 ticks in a second. And you can specify 2 things. One, the start interpolation, which is how long until the interpolation starts, and interpolation duration, which is how long the overall transformation should take. So I chose 2 seconds, and what you'll see is if we transform it, we do that same transformation we did earlier, like this, it will transform it after 2 seconds, and then during those 2 seconds it will transform to the new state. So that is basically interpolation. Now let's talk about rotations. But to do so, we need to clarify something. If I stand up straight and spin around, you probably think about it as rotation about the y-axis. But we need to rethink it. It's actually rotation about the xz plane. And this is important because rotations affect 2 axes in quaternions rather than just one. And what does that look like? Well, if we want to rotate around, say, the xz plane, like we were just now, we need to change 4 values. The x and the z in the x row, and the x and the z in the z row. And to do this, there's actually a very simple rule for any rotation. For those 4 values, and for the angle, we do the cos of the angle, the sine of the angle, the negative sine of the angle, and the cos of the angle. So if we wanted to rotate, say, 90 degrees, we would do cos 90, sine 90, negative sine 90, and cos 90. Now, the great thing about using 90-degree angles is they're always 0, 1, or -1. So in my case, how it came out was cos 90 is 0, sine 90 is 1, sine negative 90 is -1, and cos 90 is 0. So we can do a rotation now. So if I press this button, let me watch this turn, it will do a rotation about the xz plane. And it's that simple. Now, let's get into something that we've been ignoring and is very important. Scale and the w-axis. So, if we do a transformation that changes the scale, which is the very last term in the quaternion, then we'll get it appear smaller. But this is not necessarily what's happening. What's actually happening is that it's getting more distant in the 4th dimension, the w-axis. And to help you visualize that, well, if you watch as I sneak back, it gets smaller, and as I go towards it, it gets bigger. The exact same thing is happening with this transformation. It's not actually getting smaller, it's just getting more distant in the 4th dimension. And this is how scale and the w-axis all tie into 4D rotation. So if we use our same rule, but we want to use the w-axis this time, we need to change the w column and the w row. So we do the exact same thing we did there, but we just have to pick different values. So I've done that here. And one thing to note is that this matrix would end up with a 0 in the scale column. And the scale works by dividing the dimensions of the block by the scalar, this thing. So if this comes to 0, then it would be dividing by 0. And so it's going to not render, because that's impossible. So what I've always had to do is I've always had to set it to an actual number, like 1. And that's fine, because it will just help us visualize. It's just offsetting us 1 block in the w-axis. So if we do the same rotation with 1 as the last element, then we'll see what a 4D rotation looks like. And as you can see, it's a very strange transformation that I can't actually show in Minecraft because unfortunately any transformation I do along the 4th row doesn't render. The block will not be stretched in the W dimension. The game can't show that. So you just see a slice of it. And that's also quite important for what's coming up next. But that is 4D rotation, so you can choose any of the axes like XW, YW, ZW. There are 6 in 4D space. And you can rotate about them. Pretty easy. Now, knowing about 4D rotation and block display entities, we're ready to make the Tesseract, but how do we go about it? Well, we've got to think about how we would do it in 3D for a cube. And if we want to make a 3D cube, we start with a 2D net made of 2D squares. And how we would fold it into a cube is we would fold the squares along the third dimension and into a cube, like so. So it's actually the exact same thing in 4D, surprisingly. For a 4D object, you make a 3D net, and this is how it would look. Now, there's actually 260 other ways to make a net of a tesseract, but this is the easiest and most famous. So, what does folding this look like? Well, it looks like that. It can't actually be shown in Minecraft, of course. And I don't think even if I could fully show everything, it would make any sense. But essentially, that is how this model was made. I made 8 cubes, and I did 90-degree rotations in the 4 dimensions, and positioned them all into place, just like I did with the cube. So it looks something like this. And this is the model I came up with. Now, there's a few things to note about it. You can see one big red cube and a small orange cube. And you can also see what appears to be a darker cube around it. But this is actually the 6 other cubes all around it. And the reason why you're seeing this is, once again, because of the fact that Minecraft can't render blocks that are stretched in the W axis. So you only see a slice of how the block would look. But this won't matter because when it starts rotating, it will properly show its full dimensions. But in reality, these cubes stretch from the vertex of the orange cube to the vertex of the red cube in all 6 axes. Sides of the cube. So now that we have our model, we just have to apply our principles of 4D rotation. So I've just made transformations for all 8 of the cubes. 90-degree rotations in the XW plane, then 180, 270, and 360. And I just do this on a loop. So it looks something like this. And what's really interesting about this rotation is that only the x and w coordinates of each cube are changing. The y and z are actually unchanged. I know it looks like they're going up and down, but I'll explain that later. In reality, everything is actually staying the same in y and z. And this is really cool, because we can do a special kind of rotation. So, because the rotation is happening about the xw plane, the yz plane is completely free, and we can actually rotate about it at the same time. And using our matrix visualization, I can show you how that works. So we do our xw rotation, changing these 4 times. And we can also affect y and z in the same matrix. And neither will affect each other. And so if we do that, it will look something like this. And there you go. That is a double rotation of a tesseract which is only possible in objects of 4 dimensions or higher. Now, there's a couple of things I need to talk about. We'll address the elephant in the room. Yes, some cubes are sticking out of the Tesseract. And this is not due to the rotations, this is just because of translations and its delayed effect. You see, every time I do a rotation, it will rotate and it will also change position. So I have to translate it back. But the rotation always happens before the translation can complete. So some will be slightly offset, which is it's very minor, but it's noticeable. And there's probably ways around it using the teleport command, but I think for simplicity, I like what I've come up with here. And the second thing to talk about is if you look very closely, you can see the lime and yellow cubes right there. They're undergoing this rotation, but sometimes they actually go completely out of view. And this is normal. I've double, triple, quadruple, and quintuple checked the math, and they indeed do disappear in 3 axes. They are shown in the W axis, but Minecraft can't render that, so they appear to go completely invisible at the top and at the bottom. It's a very fascinating fact. It's only those cubes. But yeah, this is the Tesseract. I've only modeled XW rotation and double rotation. But I think it gets the picture across. I think it looks really cool. I'll show you from a few different angles. Ooh, the top looks nice too. If you want this in your world, then you're in luck, because I've included a data pack with all these commands. And it's really easy to run too. So first you just pick where you want your Tesseract to be. You run function 4D summon. This summons a non-rotating Tesseract. So if you want it to rotate, you just do function 4D, and you pick one of the 90-degree rotations to start with. So if you want XW rotation, you do XW 90. If you want double rotation, you do double 90. In this case, I'll do this one, and it will run the functions in a loop, and you'll get your full rotation. And if you want to stop at any point, you just schedule, clear, and you pick the one that auto completes, and it will stop. So yeah, that is the Tesseract. To finish off this video, I'd like to give some shoutouts. Firstly, if you're interested in seeing more 4D in Minecraft, there's a really fun puzzle map called the Hypercube by Flow. It was made for version 1.14, but I played it a few years ago, and it was a really fun introduction to 4D in Minecraft. It's very intuitive, and I enjoyed it a lot. If you're not into Minecraft, there's another game I've been playing recently called 4D Golf by Code Parade, and that's really fun because it allows you to get an experience of 4D from playing golf, which is really creative and innovative. And if you're not into gaming, then there's also a YouTube video I highly recommend by Hypercubist Math, which helps you really visualize the fourth dimension. And this one really helped me a lot with like visualizing how rotations worked and all that. So yeah, if you enjoyed this video, let me know. And I'd also love to make more videos in the future about 4D or more about block displays, text displays maybe. So if you're interested in that, let me know. And thank you for watching. Bye bye.